Our next talk is on the challenges in implementation of WOA, World Organization for Animal Health, aquatic animal disease surveillance standards. And who better to talk to us about this than Alicia Gallardo, a Chilean veterinarian who has spanned the divide, or the sometimes divide, between science and politics. Originally looking at the prevention of infectious salmon anemia in Chile, she then became part of the National Fisheries Association, subsequently Undersecretary of the Fisheries and Aquaculture, and is currently President of WOA's Commission on Aquatic Animal Health. Great pleasure to have you here, Alicia.
Thank you very much. Very good presentation. I like it. It's a pleasure for me to stay with you, and thank you for the kind invitation. It's my first time here, and I am very happy to see all the participation, the excellent poster. So thank you very much for inviting me to Cuthbert, for all the organization on this presentation. Well, maybe some slide will be similar to Ed, to my friend Ed, because we were together in the commission during 3 years. So at least it's a very good demonstration that in the commission we have the same diagnostic about the situation. Well, about the standards. WOA has two big documents, standards, which is the aquatic code and the manual code. So we during the I don't remember the first global conference in Norway, but we had 4 global conferences, and in each global conference, aquatic global conference, we discussed about the challenge. And I put this presentation, this slide, especially because it was in 2009, and one of the recommendations was exactly strengthening the surveillance and reporting, because this may be a continuous problem or a continuous challenge, for to speak in positive, that we need to address for the implementation of the standard. And we put about using the current system, that WOHIS is the system that all the member countries can notify the disease, list the disease, and also emerging disease. And we put about the transparency and the timely notification. So this is some part of the history. Also, after 2019, our Director General was very connected with the aquatic, because the aquatic animals are maybe sometimes not at the same level in the leadership or in the political issues like the terrestrial. So we were in a very good position, because after the global conference, we developed and participate the strategy for aquatic animal. And the strategy has 4 points. One is a standard development or update, which we were work on that. The second is capacity building, how we can connect, that you mentioned in the morning, the practical implementation of the standard. We need training, we need more simple, maybe, guidelines. And the third is about the resilience, how we can adjust our standard to the climate change scenario, implementing new standards like emergency disease preparedness and also outbreak management. And the fourth objective is the leadership. How we discuss a lot about that, how we can work and to have more visibility in the animal health world, because we need to work together. We need to work together, all the regions and the international organizations, for to be in compliance with our main goal, which is improve the aquatic animal health. So, FIO has a report every 2 years, and the last report, it was the most important report because for the first time, Sofia, for the first time, the aquaculture is more than the fisheries area resources. So the world is increasing the aquaculture. This context, and you can see the top aquaculture groups, which imply a lot of different species, but not much. Minor species concentrated in minor countries. This information is very good, and I take the opportunity to say thank you to Dr. Melba Reantazo, which, because he participated in this report and in her work in FIO. So we have challenge, we have a strategy, and we have the need to increase the aquaculture production, but in a sustainable manner. So we need these standards. We need those standards, the aquatic code and the aquatic manual. And in the case of aquatic animal surveillance, we have a special section, which is section 1, and it's contained the obligation for the members to notify listed disease and emerging disease, the criteria for inclusion, the disease listed by the WOHA for fish, for crustacean, for mollusk, and for amphibians. And the criteria, the last one is for listing as susceptible to infection with a specific pathogen, 1.5, but we have some new version of the chapter 1.4 about surveillance, and Ed participates a lot in this standard. So this standard is important, this support to the competent authority to meet the requirement for self-declaration. So WOA is promoting in the terrestrial code to get the disease-free status at a country level, at a compartment level, or at a zone level, in compliance with the information that is very clear in the chapter, and in compliance with each specific chapter, which include the requirement for all of these different categories. So we provide a table because the disease-free status is possible to get through the 4 pathways. The one is the absence of susceptible species, which is, is a table very clear, explaining maybe is focused in passive surveillance, and in a secondary manner in some cases, in some population, targeted populations, and you could go through the country or zone. The second is the historical freedom, but in that case, you need a passive surveillance and in some case, targeted surveillance to detect the clinical signs. If the environmental conditions are promoting the presentation of the clinical sign, you can use the passive surveillance, but it's difficult in some cases, and this is the reason that we put targeted surveillance. Country and zone. The third is targeted surveillance. To perform the surveillance in certain population to obtain the disease-free status. And you can go through this pathway for compartment also. And the 4 is about to, when the disease appears in a country free or compartment free, you can recover the status through the certain requirements. So we have the standard, and we have very focused in the basic biosecurity, which include an early detection system. I think in the morning, all the speakers talk about the same. Maybe this is our main point to advance. The competent authority, the capacity, build the capacity, and the diagnostic related. But what are the barriers to implement these standards? Ed mentioned, and during our discussion about the strategy, we decide, I think I forgot, it's in the next. We decide to perform a survey to ask to the community, WOHA community, about the main barriers for some standard. And we work with the 65% of the members, and mainly from Asia, participate in this survey, and we detect this kind of, we use as reference the listed disease, and we put in the last of the table the emerging disease at that time. It was in 2023, 22. And it was important because TLV, it wasn't listed at that moment. It was an emerging disease. So we asked a company, some person, some group of research, asked about the barriers. And one of the barriers is maybe the people, in some cases or in some countries, the list of diseases is not absolutely complete. It contains maybe only the listed disease, but not other disease of relevance. This is the reason that one of the recommendations is to work in the listed disease. That is included by the way, in the PMPAB of FIO, to prioritize the listed disease, to perform the biosecurity plan considering those diseases. This is very important. The other issue is if we ask to the participant in the survey about the implementation of the standard, you can see mainly they are focused in the finfish diseases. And let's see the implementation in the amphibians. Maybe it's the minor of all. And also the crustaceans. So this is a challenge. Maybe the other species than the fish are very important to address. And this is the other issue. In the web page of the WOHA, you can see this information. It's about the self-declarations. The countries has the possibility to fill a template very based in the chapter 1.4 to be in compliance with the requirements. And we don't have any free compartment. Really, we discussed during the meeting why the standards are not clear. We are proposing a new standard. Actually, yesterday on Wednesday, it was the last day of the commission, and we are in the condition to update the last version that we present to the members with more clarification. This is an issue to discuss, maybe. The other issue is not much countries are interested in to do a self-declaration. Only 4 or 5 countries. Why? Because in terrestrial, there is an official recognition of the disease status. In the aquatic, it's only to put in the web page. Could be an incentive, could be something interesting to discuss. Well, related to surveillance, at least 80% report the existence of passive surveillance in the countries, but in the targeted surveillance, the response were between 28 to 24 in amphibians standard. And the main barriers are related with the lack of financial resources, lack of human resources, and low expertise in the aquatic animal service. So again, we are in the position to highlight the relevance of the training in the surveillance elements. You can see also the PBS evaluation is the same issue. But please look at the second information, lack of knowledge about the benefits. Again, this is a standard, also is a trade, but also is about benefits, incentives. So, in general, in conclusion, the potential factors influencing are related to resources, human, financial, and logistical. The second is about expertise. And the third, it was identified as a political. Political in the sense that the leadership in the general problems of a country. Aquatic animal issues are very important. So this is maybe a gap that we need to address, and we try to do in our strategy, mainly with regional meeting, with international meeting, with networks. Maybe the networks are the most important activity related with more leadership. Well, and also the other issue that this study identified was the relationship between the lack of education and capacity building and the negative impact on the implementation of the standard. So we need training, and also it's better to consider better education. I was very happy looking some poster, including some kind of reconversion of the people to the aquaculture area to increase the education. I think it's amazing. This is maybe the way to advance in these issues. Well, sorry, maybe this is not very clear, but it's a comparison between, it's a predictive analysis, comparison, the relation with the region and the lack of education and training with the implementation of standard. And you can see the low score are related with the not much training activities. And in the region, you can see some regions more advanced than others. This is important to try to create some similar information through the regions. So in general, the countries are not implemented targeted surveillance. They have not listed diseases, complete listed diseases, considering all the risks related with the aquatic animals, including listed diseases and emerging diseases. And in the last chapter, we include the concept of the disease of relevant importance, or relevant for the country. So could be a very good idea to consider. There is a lack of laboratory diagnostic capacity in some regions, lack of national legislation, which is very important because we need the legislation for that, and in general, lack of capacity and resources. Thinking in these barriers, identification of barriers, we move to other activity of the strategy, which is the prioritization of the research. I have 2 minutes. Research activities related with the WOHA activities. And I can show that many of the prioritization were conducted to environmental assessment, to a better implementation of surveillance, maybe at the very early stage that I saw in the poster Annette mentioned, in general, The other implementation are related with the eDNA, for example, how we can go through the environmental analysis. And this information was only for finfish. We are planning to do the same for crustacean. And we identify also the disease prioritized for each, for freshwater and for saltwater. It's available for your information, and it's very useful to prioritize the standard implementation in a region or in a country. Finally, I would like to emphasize 4 issues as recommendation or conclusion of this. It's very important to promote maybe a better communication and awareness about the relevance of the notification to the WOHA and the timely notification. The second issue is to try to think and strategies to strengthen the early warning system, the passive surveillance, some kind of this app that you show in the morning, any information that support the farmers and all the other stakeholders to detect very early the disease. And in the third issue, strengthen the regional and international networks. I forgot to put the international network. And finally, this is important, share information of cases, maybe not all successful, maybe some not successful cases, but about this notification of diseases or the early detection system and the participation of the private sector. I think the PPP, the private-public partnership, could be a very good idea to support a better notification and a better early warning system. Finally, thank you very much to all the organization. Thank you to my collaborative center in Chile, CASA, and thank you to you. Thank you to all the persons that every day work with the aquatic animal health. Thank you for your valuable labor to our contribution to the aquatic animal health. Thank you very much.
So that if you have any questions for Alethea, please address them during the tea break. Thank you. You're already on the stage, Yuko. So,
yeah.
My pleasure to introduce the next speaker, Yuko Hood, who is going to talk to us about assessing sensitivity of surveillance. Very important. We have all these different approaches, and there are techniques as to how they're assessed. Yuko is a veterinary graduate who did her degree in Japan, Nihon, and has focused on policy. So she's currently a principal scientist with the Department of Agriculture, Fisheries and Forestry. And I really love these historical names. We used to have the Ministry of Agriculture, Fisheries and Food.
Forestry.
And you have Agriculture, Fisheries and Forestry. I love that accumulation. Yeah. Thank you, Yuko. The floor is yours.
Thank you, Kenton. Good afternoon, everybody. I hope you're awake after beautiful lunch again. My name is Yuko Hood. I work for the Australian Government Department of Agriculture, Fisheries and Forestry, but I'm in the Aquatic Animal Health section. Thank you for DAA 12 organizers for the opportunity to present this project. So I have a list of people there. I'm presenting this work on behalf of the project team. I'd like to especially acknowledge Dr. Robin Hall from AusVet, who actually done a lot of most of the modeling work for me. Thank you, Robin. So as Kenton said, when we carry out surveillance, it's very important to also consider how sensitive it is. So we can judge whether we are truly achieving its original objectives or not, which is very, very important. So today I'm talking about that. So before going through, just to briefly talk about background. So we had a white spot disease in Australia. So that was first detected in southeast Queensland, Australia. 2016. Following outbreak, Australia implemented a robust response aligned with the WOA code Alicia mentioned. So this is an actual article, WOA Aquatic and Animal Health Code, Article 9.9.6. So this article has a specific requirement for the country to return to white spot zone freedom from outbreak. So our key activities included delimitation surveillance to define infected and protected zone, which mentioned in the code. Next one is culling infected prawns or shrimp, disinfected farms, and following them, and we did for 18 months. Strengthened biosecurity measures, such as tightening import controls, which is very important to prevent entry of disease again. And the last one is a 2-year targeted surveillance outside of the zone, and we did that from 2017 to 2020, which returned no positive results. And 2 years later, in 2022, unfortunately, white spot disease was detected on the hatchery in northern New South Wales, which is a different state, one northern part, and it was different strain to Queensland strain. Delimitation surveillance was done in the surrounding water, epidemiologically linked water, rivers and oceans. And then we did 2-year proof of freedom surveillance, but unfortunately, just towards the end of 2-year surveillance, we detected white spot again. So we have now 3 infected zones. But for farmed populations, we can still demonstrate compartment freedom, as Alicia mentioned. And in fact, the farms are operating farm successfully and producing beautiful, healthy prawns now. Quantifying surveillance sensitivity, therefore, is essential to confidently declare freedom from white spot in Australian prawn farms. It aligns with WOA requirement. To do so, we use the scenario tree modeling. Ed mentioned briefly, so it's good. So Ed mentioned the background, but I can briefly explain again. So scenario tree modeling works like a flow chart, mapping each surveillance step where success, for example, tested negative, or a failure, for example, tested positive, can happen, then assign probability to each step. And by running this as a computer simulation, we can calculate overall chance that a surveillance will actually detect the disease. Similar to quantitative risk analysis, estimates the probability of event occurring. It's a very similar methodology. Scenario tree modeling incorporates multiple surveillance components, such as passive, active, and other things, and using existing data. So you don't need to do any extra surveillance and testing, so all retrospective analysis. Therefore, it's very cost-effective and dynamic. So we can calculate how confident we are in disease freedom based on the scope and the results. For example, we might conclude we are 50%, 80%, or 99% confidence that our farms are disease-free. So my project, we did a white spot for prawn farms, and I'll focus on the case study for today's presentation. But a second case study, we are conducting a megacytovirus in the barramundi farming industry. Alicia showed this table. I just stole from OIE code and then made it to my own format. So basically, we are doing a scenario 4. So we had an outbreak and then returning to freedom. So WOA recommends combining passive and targeted surveillance data, and then that data can be integrated using a scenario tree modeling to estimate confidence level. That's what I was doing. For white spot scenario tree modeling, we defined 4 surveillance components, along with some what-if scenarios. We have translocation testing, which is active testing for hatcheries for broodstock, and passive surveillance for broodstock, passive surveillance during a go-out, and passive surveillance during a processing. That's 4 components. And then we did what-if scenario as an active during a go-out. So this is a methodology. Analysis period was 2022-23 production cycle. For farmers who didn't respond to industry survey, data were simulated. Each component had its own diagnostic sensitivity and specificity. Design preference, we used 5% as a design preference and assumed 50% prior confidence of freedom, which is standard. Epidemiological unit was pond or tank, not farm. And any testing, PO testing was considered as additional testing of blue stock. And introduction pathway and probabilities are based on each farmer's relative risks. I think somebody mentioned that you have to map out all the farmer's location and things. We did that, and we analyzed the relative risk between the farm. But just due to time limitation, I didn't show in this slide. And also, we used experts' opinion. So that asking experts to estimate minimum, most likely, and the maximum values, especially for passive surveillance components. And after building the model, we consulted with the industry experts for critical review to estimate realistic structure and accurate data distribution estimates. So, findings, exciting. So, this is a component and system sensitivity. Component is just a 4 box, and then fifth one is a what if, and the system sensitivity is overall system sensitivity. So, PCR testing of blue stock at the hatchery was very effective with almost 90% chance of detecting infection. Because of this, extra checks at the hatchery by passive surveillance added little value since the infection was already very unlikely after the first test. Its epidemiological term is called posterior probability of infection is very low, but very difficult to explain. I hope you understand. During a grow out, passive surveillance was even stronger, 92.2% chance of detection. And then again, same reason, posterior probability of infection is very low because the secondary chance of detecting any disease is very low. So this is an overall system sensitivity. And then system sensitivity was extremely sensitive, close to 100%, and with a very high confidence, which means that if no cases are detected, our farms are free from white spot. Then we looked at our what-if scenario. Currently, we test 100% of wild blue stock for white spot as a translocation active testing surveillance. So we assessed how reducing the proportion of blue stock undergoing translocation testing would impact component sensitivity for active surveillance in hatcheries and overall system sensitivity. So compared to 100% blue stock testing, both component and system sensitivity reduced significantly. So this is a component sensitivity. So if we do 100% testing, 88.2%, that was reduced to 25.8% if half of the blue stock were tested, and further 9.4% if 20% of blue stock were tested. And system sensitivity also dropped from 99.1% to 94.8% at 50% testing scenario, and to 94.2% and 20% testing scenario. So it doesn't look very reduced, but anything below 95 confidence level is not very good in the confidence term. So in Australia, farmers are not allowed to test for exotic diseases themselves that include officially controlled disease, such as white spot disease. So we tested this scenario. What about if prawn farmers could test for white spot during a production? So we looked at qPCR and rapid antigen-based testing at monthly, weekly, daily intervals during a go-out, testing either 10 prawns from every single pond or 20% of pond on every farm. For freedom surveillance, Introducing active white spot testing during grow-out would not increase the system sensitivity. This is because, you remember, the passive surveillance during grow-out is very, very high. Therefore, value of additional surveillance during a grow-out is very, very low. Early detection model suggests that even with daily qPCR testing of every single pond, which will be very, very expensive, we would still only have a low chance of detecting a virus within 3 days. So our findings suggest that testing sick prawns or mortalities early and consistently as a way of passive surveillance is where we get the most value. To recap that presentation, so our scenario tree modeling shows that if white spot is not detected during a production cycle, we can be highly confident that our aquaculture compartment is free of infection. This strong confidence is largely due to high component sensitivity from passive surveillance during go-out. Australia's current white spot surveillance system focuses on preventing incursion from wild-caught broodstock, and our model shows the importance of maintaining 100% translocation testing, because if reducing it undermines system effectiveness significantly. Active surveillance, if permitted, only becomes useful if testing is frequent and broad, which is resource-intensive. This modeling gives us a strong evidence to support Australia's claims of white spot freedom and early detection capacity for farming sector. Scenario tree modeling also offers flexibility, allowing us to update model inputs in the future or test alternative scenarios or strategies. And finally, as I mentioned, our second case study on the megacyte virus in the Barramundi is underway. Model is built, and we are working with both domestic and international experts to finalize inputs and consult with the industry. I wanted to present that result here as well, but consulting with the industry is very important, so I just thought withhold that outcome. And then looking forward to sharing that result in the next DAA. Thank you.
Thank you, Yuko, for a very interesting presentation. Questions from the floor?
Question?
Obviously.
No, Melba.
There's a question there. Yeah. Question, fourth row back.
Hello. Madam, I was interested to know whether Australia is importing any SPF broodstock for disease freedom?
No, we don't import any live aquatic animals for aquaculture purposes whatsoever.
Okay.
Yeah.
No import at all? No import at all of the SPF broodstock or any other broodstock in Australia?
Sorry? Can you repeat again?
My question is whether Australia is importing...
No import. So it's only ornamental fish as a live aquatic animals. And then we recently approved to import sturgeon.
Thank you.
As a live sturgeon for aquaculture purposes. Thank you.
Could I ask a question as well, Yuko? What are you doing in wild populations? Sorry.
Wild populations?
Yeah.
Hope for the best. It seems to me that once virus is established in the wild population, there is a sort of a nice, little area that grows and then maintain virus-infected population. That's happening in the southeast Queensland and also northern New South Wales. Yeah. And interestingly, Queensland strain and the northern New South Wales strain is different, although northern New South Wales had a couple of different detections along the coastlines, all same virus, so 2 introductions.
The question here, second row back. Could we have the microphone? If you just hang on a sec, so everybody can hear.
Yeah. White spot virus is known to demonstrate latency related to probably some seasons. For example, in India, we have seen in the colder seasons, we have a high prevalence, and in the hotter periods, even in the wild, we don't see them. I mean,
We do, yeah.
So, in your surveillance, what if you've taken those, animals during the latent period?
Yeah, so somebody mentioned the risk-based surveillance is very important. So we did an Australia-wide surveillance in the wild prawn populations that's taken into account risk factor, which is the season, water temperature as well. So we took the samples where most likely the virus can find. And then in fact, Southeast Queensland case, we had a 2 years surveillance. And then again, we found the virus very, very end of 2 years surveillance, but we found prawn populations and crab populations more in summer as well. So the more samples available, and we tested during the summer in Australia, warmer months, tested positive. During the winter, cooler months, tested negative in the same population. That's very interesting, yeah.
Interesting, yeah. That's very interesting.
Yeah, yes.
Negative.
In Australia's situation. So New South Wales one, we found a virus, again, towards very end of 2 year proof of freedom surveillance. That was after like a warmer month in March, which is the end of summer. Yeah, and we found the virus. And then that was after big storm. So a lot of water is kind of, tumbled with the storm, mixed with the fresh water. And then we find that the sudden drop in the temperature also triggers white spot. Yeah.
Yes. So the
Okay, sorry. Can you continue? It has become a discussion, not a question. Could you continue during the tea break, please?
Sure.
Sorry, we have another question over there. Melba, I'm very sorry. The lights are blinding me, so I cannot see
It's
you. I'm
okay.
sorry.
Thank you very much, Ketan. Thank you very much, Yuko. My question is very quick. So WSSV was first detected in 2016, yeah?
White spot was first
white
detected
spot.
on the farm.
Yeah, and then it was detected again
Yeah,
some
in the
province.
ocean, yes. 60 kilometers away from the original farm.
Okay, so Australia having a robust...
Melba, can you hold the
biosecurity
microphone a little bit
policy.
closer?
Closer.
Australia having a very robust biosecurity policy, diagnostics, expertise. You have everything. What did you miss?
What did
you miss?
Oh, it's a long story, but a lot of importers are circumventing import controls. So, that was a big issue. We have a published report about it, yes. Yes. Importer is not doing the right thing.
Thank you very much.
Okay, thank you. Let's all give Yuko a hand of applause.
So the next speaker is Dr. Megha Kadam Bedekar. She is the principal scientist and head of the Aquatic Animal Health Division at the Central Institute of Fisheries Education, which is a deemed university in India. And she is going to talk about modeling the transmission dynamics and reproduction number of tilapia lake virus across various stocking densities and biomass. This is an important issue now in tilapia. So look forward to the talk.
Thank you, sir. And first of all, let me thank to the conveners to give me this platform to share my research. And secondly, I am very humbled to share my research and share the platform, common platform where all aquatic animal health specialists are there from across India, across Asia, I'm sorry. And here, dear colleagues, COVID has taught us a very important lesson, that know your pathogen, which was already discussed a lot of time. Know your pathogen right before the time, before the outbreak happens, so that you can tackle it in a better way. So that is something which I have tried to assimilate here in this research of mine, the work of mine, where I want to share with you the modeling and transmission dynamics, especially the reproduction number of tilapia lake virus across varying stocking density. I have kept it very simple with the basic formula so that not to complicate much for understanding. So first of all, let me introduce, I have come from Central Institute of Fisheries Education. It's a part of ICAR, where students from all over India and other countries come to pursue their higher education in fisheries, especially PhD and masters. And this is my team of aquatic animal health, environment and health management. And our laboratory is nationally accredited laboratory for testing of OI pathogens for shrimp and fish. And these are the research areas where our lab is working, starting from the pathogen discovery up to the environmental bioremediation of whatever happens in waters. So taking up this further, I have shown some results of tilapia lake virus disease here. These are some of the papers. Our lab has been working with tilapia lake virus from 2019, and these are some of the works which either done at our lab or CIFE has been part of the research. And now this is named as tilapia virus, of course. Why I have taken tilapia lake virus as the model here? Because tilapia lake virus entered in Maharashtra, the state where I belong, where CIFE is there, right at the time of COVID in 2019. And the pattern, if you see, the tilapia lake virus which it has followed is, it was first reported in 2018 in one state of India. And by 2022, it was already spread in all over India. And now we are already telling that it is an epidemic for India. So that has been the most ideal viral disease for taking up the example of as the dynamics. So here, I am going to talk about the R0 number. R0 number is what? The term has been most cited at the time of COVID after the real-time PCR was the R0. R0 is a mathematical term that indicates how contagious and infectious a disease can be. When your R0 is less than 1, the disease will be likely to die out. When R0 is equal to 1, the infection will stay stable. And when R0 is more than 1, means there is a potential for disease to assimilate, or there is a potential for being outbreak. And if you realize this picture, this I have taken from Ebola and SARS, and if you realize there is a patient 0. Patient 0 is someone who is already infected. That will not be called as infected. Yeah, there is a patient 0, which will be infecting others. The others will be called infected. And if you realize here, R0 is, for Ebola virus, R0 is 2, because patient 0 can infect two persons. For SARS, R0 is 4, because patient 0 can effectively infect 4 people. So that is the strength of R0. And based on R0 studies, if experimental studies are done, based on experimental studies, we can extrapolate what will happen in other conditions. See, this R0 is basically defined for the terrestrial animals. If I talk about terrestrial animals, what happens? There is a 180-degree platform and 4D of infection is there. The environment which is available is 4D. But when it comes to fisheries, we have not the 180-degree platform. We have a 360-degree platform, and chances of infection go up to 12D. So definitely infection assimilation is far, far more multiplied when it comes to aquaculture or fisheries. So this is my experimental trial, the very basic experiments which are done in lab. Basically, this was with the tilapia lake virus. The first experiment which was done was with the LD50. If you can see, the size of fingerlings were 4 to 5 grams. And density is the basic density, that is 100 fingerlings per 1,000 liters. And the dose which was used is LD50 for the basic infection, to judge how the infection happens. And the duration of study was 14 days. This baseline was used for extrapolation for stocking densities and cohabitation, which I'll share in my next slides. These are the methodological framework. As I said earlier also, this is the very basic methodological frameworks. There are improvisations have been introduced, but that will confuse the study. That's why I have taken very basic here. So we have used here dose response, that is infection probability model. Then SIR, that is the very basic model for R0 identification, that is susceptibility, infected, recovery model. And then there is an attack rate and scaling law of extrapolation when I want to use my baseline data to extrapolate other studies. Yeah, this is just, I'll go through the formulas, what we have used. Dose response probability, where beta is saying transmission rate, I is the number of individuals infected, D is duration of exposure, and N is total population. Mind it, N is always part of the formula. SIR is basically how to calculate R0. This is BCDR, where B is transmission probability, C is contact rate, and D, which is included here, is the duration of infectiousness, which we have taken here for 14 days time. Attack rate is based on, again, S is the number of susceptible at start, and N is the population size. And scaling law means when I am using the baseline R for the scaling up of the research, where there will be a contact rate for the new number, and there will be a new N, new population, and new contact rate will be included. Then there will be, the scaling law will be there. So this, with this background of the mathematical formulas, this was the experimental anchor for us. 100 fingerlings when are taken, a design for 100 fingerlings, which I showed earlier also. Probability of infection, when I am using a LD50 dose of virus, the probability of infection is 93%, attack rate is 90%, and R0 is 37%. This is based on or confirmed with our PCR result, where the pool of 100 fish, around 93% fish will be infected. So please keep in mind that this is based on the PCR result. I have not included the clinical cases here. What was the percentage of clinical cases, just to avoid the confusion here. So this was the basic. If you can see, the graph will be on exponential, and R0 will be very high if LD50 dose is there in water, that is 37 R0 is there. Interpretation, it confirms the high transmissibility in the fingerlings. The same data were extrapolated for fries. Here, scaling density is 30x, because now this is 3000 fries. So extremely dense condition, what will happen? There is 30x is the density, and contact rate is also 3 times to the basic. And in such situation, a flat R0, if it is calculated, it is 1300. That means one infected model can infect 1300 surrounding fish. So interpretation will be extremely high epidemic potential in case of hatcheries. And when 40 to 60 adults are there of around 800 grams, at that time again, because the load of virus is high, LD50 load is there, infection probability is around 50 to 70%, and R0 will be somewhere between 20 to 46. Epidemic is possible, but at slower rate, because larger fish have less transmission of disease. So this is the graphical comparison of same, and this is the comparative summary of my results for the first, which is done with LD50. That was just to understand how I can go with the R0 studies. This is what really happens, a true infection, a cohabitation challenge. In this setup, 1 by 10 is the seeding, like 1 infected fish is introduced for cohabitation against 10 fish. So in that case, the observed secondary infection, that is PCR based test, positive test, were 13 positive tests, and derivation was like, because 13 are positive, attack rate is 0.13. When attack rate is 0.13, the extrapolation will reduce, the chances of infection will reduce. 3000 fish now will be having a R0 of 12, still at highest chances. Still for hatcheries, this infection has a higher chances of happening, but in adults and in the fingerling situation, the contact rate is less, and R0 is also very, very less. And if infection happens in this situation, in cohabitation stage, if infection happens at this rate, definitely infection is going to die, which is the prediction, which is not determination, it is the prediction. This is the summary of cohabitation challenge. If 100 fish are there, 13% is infection probability, and here R0 is less than 1, that is 0.14. So if cohabitation at 1 on 10 is happening, our R0 is less, and prediction of outbreak is comparatively less. But if density is very high, still there is a chance of outbreak because R0 is around 12.6 here. So this is the plot for cohabitation. When 100 fish are there, it's a flat curve at R0 of 0.14. 3,000 fish, it is steep epidemic rise up to 12. And at 40 to 60 adults when are there, a negligible spread of infection will be there. So these can be the important pointers to understand that how an infection like TILV, which has become epidemic, can be there. Why? What is the importance of doing R0 here? First of all, it will give you a threshold indicator based on which you can decide what I can predict. And there is a comparative risk assessment group can be created. It can guides management, and you can extrapolate the potential what can happen in future if such disease comes. And this is the significance of my study is that we could understand the TILV dynamics and risk stratification can be done. It is a benchmarking, and of course, it can have an application to support the stocking policies. These are the basic significance of studies. I have given a short comparison with what COVID data is available. You see, based on what COVID data is available, COVID-19 had a R0 of 2.5. Still, it has the massive impact. When it comes to the water system, as I said, 360-degree, 12-dimensional chances of infection, the same thing increases to very high, up to 37 or 1300, like that. So definitely those are not measurable values, but yet you can extrapolate, you can understand, you can know your pathogen's impact. Okay, finally, this is the last question from my side. Is R0 constant? In theory, when infinite population is there, a well-mixed population is there, definitely R0 is constant. In practice, fish experiments, tanks, cages, situations, whatever is there, R0 changes with density and tank consideration and other consideration because contact rates are not independent of N, that is population. So if population changes, dynamics or R0 will also change. So yeah, that is all from my side about the R0 or transmission dynamics. What I want to add it here that since we have learned already a lot from COVID, of course now the research which I have presented here was based on TILV's PCR test. PCR positive cases, but what I have not included here is more important. When TILV is always something which can show up any time as an infection when there is other environmental or other cohabitation, other co-pathogens are there. So in that case, definitely this PCR tested are going to play an important role, and I hope this R0 study will help us to understand the dynamics of transmission of diseases. Thank you so much for your patient hearing, and my acknowledgements to organizers of DAA and director of CIFE, and of course funding from NASPAD Referral Lab Project, Department of Biotechnology, and my acknowledgement to all faculty and students and research fellows who are involved in TILV work. Thank you so much.
Thank you for this very interesting data. Are there any questions? Okay, maybe then you can discuss later. With people,
could I just make a comment, actually? And that is that one of the assumptions, as you said there, is that you've got homogeneous mixing of the population, like Brownian movement, and that works very well within a pond.
Yep.
But between ponds, you have a very different situation where you have network connections.
Yeah.
And in those networks, the concept of R0, as you've described there breaks down a little bit. But
Yeah, maybe in that case we have to do the back tracing of the work. Yeah. Thank you so much.
thank you very much. Our next speaker, please. Our next speaker is going to talk about the prevalence of Edwardiella tarda, an antimicrobial resistance in Indian freshwater fish farms. And the speaker is Gaurav Rathore. Gaurav is a principal scientist, a veterinary graduate from GB Pant University. He's did his MFV Masters at Itsatnagar and his PhD in Lucknow. So,
Thank
floor
you.
is yours, Gaurav.
Respected chairpersons and dear audience, and many of them are my students also sitting here. Today I'll be talking about our work on Edwardiella tarda prevalence and antimicrobial resistance in Indian freshwater fish farms. This is our team, and I am just presenting the work done by the entire team. I will not talk about much about global aquaculture, but India is the second largest fish producer in the world. And in the freshwater sector, we have got two major commodities that are contributing to aquaculture production. One is the Indian major carps, and the second one is the pungaceous culture, that is the emerging freshwater species in India. And both of these, the production systems, they are facing challenges of the disease. The challenges are more in the pungaceous, which is the emerging sector, as compared to the Indian major carp farming. So we were interested to study both the sectors and identify the pathogen, what are the pathogens present and what are the factors that affect the prevalence of a pathogen. So are there any factors that are important, so that we wanted to understand both in the carp farming as well as in the pungaceous farming. Edwardiellosis, if we want to understand what were the research gaps available in this field. The pathogen Edwardiella tarda is not a new pathogen to India. It has been worked out quite extensively in the past as well. But our concern was that there was, if anybody talks about what is the prevalence of Edwardiella tarda in our farming system, so there was a gap. We did not have the data on the prevalence. Then there was the lack of data on its economic impact and what conditions actually provoke the outbreak of the tarda infection in either pungaceous or in carp farming. So the objective of the study was to estimate the prevalence of Edwardiella tarda in freshwater fish farms, identify the risk factors associated with its prevalence. So why we were interested in this? Because we wanted to know what is the proportionate role of Edwardiella tarda to overall disease burden. How much contribution does Edwardiella tarda in the disease fishes is there? What is the proportionate contribution? That we were interested to see whether out of 100 disease fishes are there, so what is the proportionate contribution of Edwardiella tarda in the total disease burden. And we were also interested to understand the risk factors so that we can, those risk factors can help us in the disease management. So our material methods was that we did the study for around 1.5 years, and our target area was spread extensively across 3 states. And these three states were chosen very carefully which form the bulk of the aquaculture production in India. So we divided the study area into three regions. One is the northern region, the central region, and the southern region. So here, they are all big states of India. One is the Uttar Pradesh in the northern India. Second state is the Madhya Pradesh and Chhattisgarh. This we combined as a central region. And the third is the Andhra Pradesh, which is a big contributor for the aquaculture production in India. So in our study, we studied 227 fish farms from all the three regions together. If we try to divide this numbers, 227 fish farms, it was divided into calf farms. We studied 142, and the Pangasius farm were 85. So this study was done without any bias across the study regions. So whenever we went to a farm, we tried to categorize the farm into two on the basis of the health status. So on the basis of the health status, out of the 227 farms, 37 farms were of the Pangasius, they were belonging to the diseased category. And carp, the disease incidence was low. That is, only 12 farms out of the studied population were categorized into this category. So what was our case definition? My guru and guide, Dr. Kenton, has taught us that you should always begin your study with your case definition. So we wanted our case definition to be studied as on the basis of visual assessment as well as farmer interview. So whenever we went to a farm, we did the sampling of the fish, and then we examined a haul of the catch, and then it was visually assessed for the symptoms like ulcers, red spot, hemorrhages, bulging eyes, or swollen areas, or frayed fins, or dropsy. And the farmer was also interviewed for other symptoms like whether there is a loss of appetite, whether the fish is consuming the desired feed or not, or there is any kind sort of rubbing so that any parasitic infection is there, or lethargy, or erratic swimming is there, or increased mucus or morbidity is there. So if at all the farmer or the visual assessment was there, then we classified that farm as the diseased farm. The farm which did not have any of these symptoms, it was classified as healthy farm. And in addition, we also had a questionnaire. And this questionnaire also was included about the stocking density, whether the biosecurity measures are in place in the farms, or what is the feeding, whether the farmer is giving the pelleted feed or the farm made feed, all these questions, what is the yield, and what is the health status. So this is our data collection at each farm. So like this, we did the interview and we surveyed 227 farms. And what was the methodology? Once we came out from the farm, at each farm we collected the sample on two bases. One is the health. If the farm was healthy, we took the gill samples, and if the farm was categorized as deceased, then we took the samples from the kidney. We brought this in the transport swab and brought to the laboratory. And there is a technique that is for the tetrathianate. Normally it is for the isolation of the salmonella, but we used it for isolation of Edwardsia tarda. Then this is our methodology, and we did the bacterial isolation, molecular confirmation by the FIMD gene PCR and SORT-B gene sequencing, and that's how this was our material methods for isolation of Edwardsia tarda. And then whatever isolates we got, we did the disk diffusion method using the for the AST, and we used the 10 classes of antimicrobials for the testing of the AMR profile of the isolates. And then thereafter, whatever pathogens, whatever the isolates were resistant, we screened them to study what is the mechanism of antimicrobial resistance in these isolates. So these are our results. Out of 227 farms, we could isolate Advertiella in 35 fish farms. And whenever you isolate, you can pick one isolate or 5 isolates, but we picked only one isolate per farm. And these isolates were identified by Vitek2 system, and thereafter they were confirmed by the PCR amplification of the FIMD gene and SORT-B gene. And then some isolates were randomly selected and sequenced by Sanger sequencing, and the BLAST analysis showed that 99.75% to 99.90% homology with the corresponding gene sequences of Advertiella tarda in the gene bank database. And this is our phylogenetic tree. When we try to analyze where our tarda are matching geographically. So our group of tarda isolates, they were closely matching with the isolates reported from United States. And they were quite distant from the Advertiella piscicida. There is a controversy, or there is another school of thought going on that the Advertiella tarda and piscicida, tarda is a pathogen of humans and piscicida is for the fish. But in our study, the isolates, they are clearly grouping to the tarda isolates, not to the piscicida. Now this is the interesting part. So the pooled prevalence was 15.41%. And when we try to see the comparison between the Pungaceous and the calf farm, the prevalence was significantly higher in the Pungaceous farms as compared to calf farms, 24:9. So that was quite high. And when we try to analyze the results between is there any difference between the prevalence between the size of the farm and the prevalence, then the farms with the higher size, that is more than 2 hectares, there the prevalence was significantly higher as compared to less than 2 hectares. And when we try to see the geographical differences, whether there is any significant difference between the geographies, you can see here in this graph, southern region and central region, they have got higher prevalence as compared to northern region. And we also wanted to see what is the effect in the different seasons. So we did the sampling in different seasons, different months also. So you can clearly see here in this graph that the tarda prevalence is more common in the summer months as compared to the winter months. So this is again another finding. Now this slide is very, very interesting. This slide shows that in the diseased Pungaceous, if you sample 100 diseased fish, Pungaceous fish, out of 100 diseased Pungaceous, 54% Pungaceous fish you can isolate Advertiella tarda pathogen. This is from our study. And as compared to healthy fish, the prevalence is very, very low as compared to diseased fish. And now then what is the status between the AMR profile of the 3 regions? So here you can see out of the 10 classes, our antimicrobial resistance was only seen to 3 classes, fluoroquinolone, tetracycline and sulfonamides. And significantly higher AMR was found in the farms of the southern region as compared to other 3 regions. And you can see here, this slide again shows that only the isolates from the diseased farm, they have got higher AMR as compared to the isolates from the healthy fish farms. Then significantly higher AMR was seen in the Pungaceous farms as compared to carp farms. So what all these, if you club these findings and you try to analyze Pungaceous culture, and then these are the ARGs which we detected, and this is my conclusion. based on this study, we think that the Edwardsiella tarda is a pathogen of concern for the Pangasius fish, and the Pangasius farm in the southern region, they have got higher prevalence of E. tarda during the summer season, and significantly higher AMR in Pangasius farms of central and southern region, and especially those which are affected by the disease. So if we want to do surveillance, targeted surveillance for E. tarda, then the southern region and the Pangasius fish should be our choice of the surveillance. So this is all about my research work, our teamwork. Thank you so much. And I wish to thank all the organizers for giving me this opportunity. Thank you.
I open this talk for questions. If we have two microphones, can the second microphone go to the next question? Edmund.
Thanks very much. I wondered what advice you would give to farmers who are currently free of Edwardsiella in order to, protect their status.
I could not get you.
Oh, sorry. So from your study, it's clear that many farms might well be free of Edwardsiella. So what advice can you give in order that they remain free of the bacteria?
Actually, I have not presented the full data. We also analyzed the risk factors, and our risk factors included implementation of biosecurity measures. So the farms, wherever the biosecurity measures were in place, there the Edwardsiella tarda infection was significantly lesser. That came out clearly in our study. So whenever we used to go to the Pangasius farm, we always told them that you have to implement the biosecurity measures. So that is very important. So that part only we emphasized in our advice to the farmers.
Any other questions? Thank you, Gaurav, for keeping well to time and for an excellent presentation.
So the next speaker is Dr. Anupam Prachumwat. He is a senior scientist at the National Center for Genetic Engineering and Biotechnology in Thailand. He did his PhD from University of Chicago on molecular evolution and gene duplicity. And today he's going to talk on the database of endogenous viral elements in peanut shrimp genomes for enhancing viral PCR-based detection.
I thought I went to check.
Dr. Anupam.
You can switch.
Okay, so this is some time is needed to upload his presentation. We will invite the next one. Yeah. Okay.
So the next, we're going to switch to the next presentation while the person who was supposed to speak now uploads their presentation. So the next presentation will be molecular prevalence of protozoan pathogens in farmed and wild bivalves from the coastal waters of India. And the presenter is Krupesha Sharma, principal scientist at Cochin Central Marine Fisheries Institute, who's is another veterinarian from Bangalore, did a master's in veterinary pathology and a PhD in shrimp pathology in Karnataka. Floor is yours.
Thank you, Kenton. Good morning, good afternoon to all. At the outset, I would like to express my gratitude to the organizers of DAA 12 for giving me an opportunity to present our study here. In the next few minutes, I will be sharing our disease surveillance results on bivalve pathogens conducted under the National NOSPAD Phase 2 during the last 3 years. As we all know, bivalves like the green or brown mussel, the oysters and clams, they are the source of animal protein. In addition to that, they are involved in maintaining the integrity of the ecosystem, as well as because of their filter feeding and sedentary nature. They are widely used in various biomonitoring programs across the globe. These bivalves get infected with certain pathogens, especially the protozoan pathogens, as indicated yesterday by my friend from Japan. And some of these pathogens, protozoan pathogens like the Parkinson's, the Martilia and Bonamia, they affect a wide variety of bivalve species, causing considerable mortality. Hence, these pathogens are currently under surveillance by the World Organization of Animal Health. So it has already also been reported that the global warming and also the trading of bivalves across the borders are the main two reasons for the widespread expansion of these diseases in case of these bivalve mollusks. As far as Parkinson's is concerned, this Parkinson's has linked to considerable mortality of the formed green mussel in India. And many of these pathogens, they are transmitted horizontally and in a high density aquaculture system, making this management of diseases quite complicated. With this background, the objectives of the present study was to update the molecular prevalence of certain key pathogens like Bonamia, Martilia, and different species of Parkinson's in Indian bivalves, and also to compare the prevalence in wild as well as the farmed bivalves, and provide the baseline data for the management of these diseases. So our study area was the east coast and the west coast, whereas most of the samples were drawn from the west coast because our study mostly targeted the farmed bivalves, and the Kerala is the state where most of these bivalve farms are concentrated. However, we have also drawn samples from different species of wild bivalves. During the last 3 years, that is some 22 to 25, we have sampled around 4,700 bivalves from the bivalve farms, and also around 2,500 bivalves from the wild stocks. So here, the farming is done during the months of November to May, and we collect the samples from the bivalve farms during this period. Whereas in case of wild bivalves, we collect the samples round the year. And the bivalve farms is constituted mainly by Perna viridis, and hence the samples of Perna viridis alone were obtained from the bivalve farms. However, in case of wild stocks, we have mainly collected the samples from Perna viridis from the wild, and different species of clams, and also edible oyster, in addition to several other species of bivalves. And the methodology adopted was as per the WAH guidelines, like the PCR, the RFTM, and histopathology. And in case of RFTM, that is the race fluid thioglycolate medium, here we can see the blueback hypnospores, which are thick-walled. But the disadvantage of, even though it is a gold standard, the disadvantage is that you cannot differentiate, identify at the species level, and also it is time consuming. It requires more than a week to get the results. And in case of histopathology, in case of Parkinson's, you can demonstrate the tropozoites, the signet ring-shaped tropozoites. And the advantage is, here also the disadvantage is that you cannot differentiate the species, but the advantage is that we can identify, we can see if there are any other pathogens are present. And the molecular methods we are widely using the OAE protocols. So based on this RFTM and PCR, infections with Parkinson's behensis and also infections with the OAE listed pathogen, that is Parkinson's Wolseni, have been reported from the formed as well as from the wild bivalve stocks. Also, we have encountered mixed infections consisting of both behensis as well as Wolseni from several states. And we have not detected the presence of other protozoans like Bonamia or Martilia, and also Parkinson's marinus. So this is the, these images shows the mortality associated with Parkinson's during the last 2 to 3 years. Here we have encountered, this is in case of formed bivalves. Here, the infections were normally seen in the warmer months. And also this was, the mortality was indicated by gaping and the loss of the mortality up to 70%, and the meat was thin and watery. So here the habitat-wise prevalence, you can see the formed, in case of formed bivalves as well as the wild bivalves, the prevalence of behensis was much higher than the prevalence of Wolseni. So, as far as the season is concerned, it is whether it is a overall prevalence or the in case of formed or wild bivalves, the prevalence was more in during the warmer months of the year, like from January to May. And as far as the year-wise prevalence is concerned, even though the formed and bivalve, it is quite similar, we can see that the prevalence of behensis is increasing, while the prevalence of Wolseni is decreasing during the last 3 to 4 years. And the species-wise prevalence, of course, I have already told that our samples were mostly drawn from Perna verdis. But here the prevalence of this bengalensis, G. bengalensis, it may be slightly biased because the number of samples were very low, it's around 4. So we can say that the formed Perna verdis were more susceptible, or the prevalence was more in formed Perna verdis when compared to the wild one. And coming to the spatial prevalence, again, here we can say that in the state of Kerala and Maharashtra, in case of formed bivalves, the prevalence was high. Again, this is quite biased in case of Maharashtra because the formed samples were very less. So, the most of these bivalves forms are concentrated in Kerala, so naturally the prevalence was quite high. So, these data, suggest or highlights that the Parkinson's is a silent killer lurking beneath the Indian waters, threatening the bivalve farming or affecting the expansion of the bivalve farming. In India, this behensis was first reported in Casostrea madrosensis, but without any mortality. Since it has got a direct life cycle, it facilitates their rapid spread. And it has been reported that the infected bivalves may release low number of parasites, but when the bivalves are dead, they pose a big problem to the local bivalve population. As reported here as well as in the previous studies, high temperature favors the proliferation of these high temperature as well as high salinity favors the proliferation of these parasites. And bivalves, since they are filter feeders, the stress due to adverse environmental conditions may make them susceptible to the diseases, because we have seen that Parkinson's positive in many cases without any mortality. And wild populations may act as the reservoirs, and also the movement of bivalves also may pose a risk in dissemination of the infection, because the bivalves are harvested from one state and they are transported to some other state, and before they are sold in the local market, they are kept in a water body for quite a number of days, leading to the contamination of that particular water body. So the infection can cause significant mortality, but it depends upon the species of the Parkinson's and also the host, and in addition to other environmental factors. So early and accurate detection using these molecular techniques is very important for any intervention. So the strict biosecurity measures, like mostly the preventing the free movement of bivalves, is very much essential to control the spread of this infection. And another important observation is that since this highly invasive species like this Trigata, we have found that they are also the carriers of this Parkinson's, so they may lead to the rapid dissemination of the disease. So to conclude, these molecular tools revealed that the Parkinson's was very much prevalent in the formed bivalve population. And when we consider the highly pathogenic nature of this organism and the very broad host range, this presence of this Parkinson's is really a disturbing factor for the expansion of bivalve mariculture. And also, when the regular monitoring is absent, it may also lead to under-reporting of the diseases. So the future research should focus on the pathogen-host interactions and also the robust correlation between the environmental factors and the occurrence of disease, especially using the hatchery-produced bivalves, in addition to the climate change impacts. So I acknowledge the Director CMFRI as well as the NASPAD for conducting these studies. Thank you very much.
Thank you, Krupasha. Any questions? No questions? Okay, thank you for keeping so well to time. Thank you.
So now Dr. Anupap's presentation is ready. So we invite Dr. Anupap back.
Okay, thank you very much. So missing the file make me even more excited to share our work with you. Okay, and first of all, I want to thank the organizing committee that allowed me to come to share our work with you. Our lab have been working with endogenous viral elements for quite some time now, and you have seen that on the second day of the talk during the shrimp disease session. Okay, and actually, so I came from National Science and Technology Development Agency in SCDA or NASA that Dr. Karaya has already introduced you on that day. And also, I'm also located at Centric Shrimp, a Faculty of Science, Mahidol University. And without ado, I would like to thanks again, give this acknowledgement to this agency for funding to support our work that I'm sharing with you today, and especially CAS and NASA Joint Research Program that allow us to do this work, and several people who helping and sharing this work that I listed here, and especially Dr. Timothy Frego, Dr. Kaya Sijun Laksana, and Professor Fu Chao Li, and Professor Huang Jia. The topic I will cover today will be on EVE. I will touch briefly, and then EVE with the false positive PCR detection and the database that we're trying to produce, establish, and how this EVE information will help us to improve the viral PCR detection method. So endogenous viral element, actually I'll not touch much, but actually it's kind of under the Professor Timothy Frego about viral accommodation. Actually, this is pieces of inserted virus genome into the host, which is our case is shrimp, and it's a path record of infection, and it's a reservoir of potential immune memory. Okay, that's one of them. I'm not sure from here. You can see that this EVE may be producing here, and then double spread that we already mentioned, and then this kind of EVE may be, can control the viral genome or degrade them, okay? And this kind of piece of application will help us in terms of apply in terms of control infection. But there's another case that you have non-protective EVE, the piece of element that will have this EVE in the genome of uninfected shrimp and will have positive test effect from the PCR. And these positive cases from the result will disrupt international shrimp trade. So identify EVE will help us to improve the VOA PCR detection method, okay? And recently that we found that there are evidence of EVE in several of these shrimp genomes, okay? And that's already mentioned, but I will touch upon this kind of to review that mentioned about the false positive PCR that detected in this two review. And then I will show you the cases that we recently found, which is DIV1 EVE in P. vannamei and also Mycobacterium rosenbergii with it. Dr. Jirapon is already presented on that day, but I will recap you briefly that we detected DIV1 ATPS positive PCR on these two shrimp from our surveillance, and it's really high number of PCR positive, but these shrimps actually healthy, and then production from these ponds that we survey is appreciable, so it's no deleterious into all these shrimps. And we use these shrimp, and then we did the sequencing at the end from these from the shrimp sample. We did about these 27 million read, okay, and we found that the read number that could mappable to the DIV1 genome is only 600, okay, very, very low pieces. And this x-axis is the position on DIV1 genome, okay, and the y-axis you don't see clearly is number of read that mappable in this region. You can see that some of them, they're missing, okay, so there's no intact of the DIV1 genome at all. And the highest number is 8 read per region, okay, which is, we found that this ATPS PCR positive have been found recovered from this sample that we detected, and it support the PCR. And we think that it's from the EVE. And also the recent publication from our group, actually Dr. Gaya is the first author in here, and they say that this case on IHHNV has not resulted in significant consequences, for example, production losses, morbidity or mortality at the zone or country level in Thailand since 2010. Okay, this is one of the information. And I will show only pieces of the result that they have, which is y-axis is positive of IHNV detected in the sample by DOF, and the y-axis is production. You can see the positive correlation on this data. And the point that they found is that all of these have high positive of the IHNV detection in several of the samples, okay? And it's high. And they tested with other stuff, so it's kind of showing that they came from mainly from positive. And okay, I'll talk about database construction. So basically, we want to identify EVE, which is we have the genome and proteome of shrimp and viruses, and then we do database construction and put these EVD that we identify into database portal. Okay, and the identification of EVE, we're using viral proteome and genomic against of the decapod. Okay, we use BLAST-X and BLAST-N and combine the result. The BLAST-X result, we use it from these references. And in this case, we use 5 WSSV, IHNV, DIV1, YHV, and TSV, and 13 decapod genome from these 3 species. Okay. And we hope that we will be able to let you search this result. Cannot see very clearly. So this is using the text search based on, for example, the gene. You get this information out, and then when you click on each of the individual record, you can bring you to the sequences of those particular positive EVE in the database, okay? And this is still internal construction. We hope to share with you a public release soon. And kind of this is y-axis is the shrimp viruses, DNA virus, WSSV, IHNV, DIV1, okay? And then this YHV, TSV, these RNA viruses. And the y-axis is number of EVE we found in each of the pairwise comparison between the virus genome versus the shrimp genome. You can see that remarkably found a high number of EVE on the DNA database, DNA viruses. But for RNA viruses, I think this is kind of false positive of this detection. We don't think that we could detect only RNA viruses in the shrimp genome here, okay? And if we use this information, we hope to improve the viral detection. In this case, we want to show you that on the white spots syndrome viruses. So we have this region on the WSSV EVE, okay? And then we can use this information to produce the region of non-EVE on the virus genomes. And then we can check the conserved region and then decide primer for all of the isolated white spot viruses that are available in GenBank. And then we can decide and then do test the sensitivity and specificity for this. And then we're still doing this cases we hope to share with you later on in our publication. But we have one case that I will give you an example. Would be in Thai DOF now because Thai shrimp production has been reduced. So DOF allow us to import the frozen shrimps from abroad. So we found the frozen shrimp that have white spotted contaminated with it. And then we also have the isolate that already widespread in our domestic. So we want to compare this, and then we sequencing this genome. We found that there's differences in the term of between these two strains in the non-EVE region. So we decide primer and then to do candidate and test their sensitivity to specific of the two strains here, and then test for sensitivity as well. So this is a case of this is the primer that detecting capsid protein that we detected both the strain sample of the shrimp that infected with the imported and domesticated, but of course for the uninfected we didn't get any result. But we compare the one that specifically for the imported white spot, we see that this is showing the pizza product. And vice versa for the domesticated strain, we see the product as well. And on the non-infected, we see some of the non-specific band, but not the target one. And since test with the other pathogen, of course, we couldn't find it for both of these two primers, okay? And when we test sensitivities, we found that for the one that imported get to about 100 copies of the WSSV. And similarly for the domesticated one, around, I'm not sure which ones go to 10. This 10, and this probably 100 copy. Okay, and we hope to use it to help the importer to distinguish or sample their imported shrimp. Okay. And the take-home messages that I'd like to tell you that we are still developing these EVE databases, and these EVEs still characterizing it. And we focus on these 3 economically important prawn sample and these 5 viruses. And the rest, I will just show you that will help improve the PCR detection method that avoid the false positive from the EVE present in this shrimp genome or even in other sample. And this is the last one I would like to join. Take your phone and take the picture and join us for this international training course for biology and pathology of the peanut shrimp. And then this year will be around middle of November, okay? Send us this email. Thank you, August, for taking photo. Okay, thank you very much and for listening.
Thank you very much for a very informative talk. Just a general question, do we find these EVEs for other viral infections? Is it a common sort of outcome of post-infection with viruses?
Could you repeat the question again?
Okay. Are these EVEs, are they common in all post-viral infections or just the ones that you've been studying?
Are they prevalent in all of what?
In all sort of post-viral infections, so not just white spot or IHHMB.
In other hosts?
Yeah, or in any other host. Yeah.
And our collaborator in CAS, they use more of the crustacean genomes. And they found that originally of these coexistence between all infection, for example, the IHNV. And recently we found that there's some very recent insert in certain populations, so they'll have different pieces of these insert into their genome. Actually, and some of them could present in only one population or not. And most of the EVE that we found here, most of them are ancient, especially white spot in genome in these publicly available crustacean or shrimp genomes. Yes, thank you.
Right, thank you.
Thank you.
Thank you very much. Any further questions? I can't see anybody.
Okay.
Oh, yes, thank you.
Hello, thank you for this very interesting topic. Regarding AVE, when you find AVE, indigenous viral elements, are they in the sequence is enough to identify are they transcribed, are they become like proteins? And if they are, yes, if that length is enough to produce a protein eventually, is it a core protein? Is it a protein with a virulence factor, or it is just of unknown? Because as we know that regarding WSSV, that it has more than 400 or something like this, and some of them with unknown till now unknown function. So are there?
So if I recap your questions again, you asked whether all these EVE will transcribe and producing protein, and what type of protein they are. Actually, we haven't had that cases of the EVE producing protein, but eventually cases could be possible that will create a new gene or something. But in our case, we found that these EVE produce transcript. And if the EVE is expressed, but we don't know whether they produce protein or not, it can protecting the host, which is shrimp, to viral infection. So that's what Dr. Suparat had been shown in the second day of his talk.
Okay, thank you.
Thank you.
Any other questions? I'm sorry if I miss you. I'm blinded by the lights here. Thank you very much indeed.
Okay, thank you very much for listening.
Our next speaker, actually, I think for me is the tip of the trunk of the elephant in the room, in that it's the only talk on zoonotic parasites that we have in this conference. And given that the estimates are that 50 million people worldwide suffer from fluke, and we're going to hear about anisakis in a minute, I hope that the next conference I come to, there'll be a whole session on zoonotic parasites. But it's my pleasure to introduce Mazazura Rahim, Senior Scientist at the Fisheries Research Institute, Penang. Mazazura combines two very favorite traits of mine, laboratory skills with field work. And she's going to talk to us on the, let me get the title here, the epidemiology of anisakis larvae and farmed fish within aquaculture zones of Peninsular Malaysia. The floor is yours. Thank you.
Thank you, Dr. Canton. Assalamualaikum, namaste, and a very good afternoon, ladies and gentlemen. My name is Mazazura Abdurrahim from Fisheries Research Institute, Penang, and I'm standing here on behalf of my colleague, Dr. Kwa Beng Chu, who cannot make it today. It is my privilege to present to you our study entitled Epidemiology of Anisakis larvae in farm fish within aquaculture zones of Peninsular Malaysia. Okay, we are here since 9 a.m. this morning, and I think we have mentally tired, right? So let me ask my little cute worm to wake you up, if it's possible. Yeah. Okay. Anisakiasis is a parasitic disease that caused by nematode larvae of a genus Anisakis. And this parasite is commonly found in marine fish and are of increasing concerns due to their zoonotic and allergenic potential. And while the occurrence of Anisakis larvae is well documented in wild-caught fish, information on their presence in farm fish remain limited. And the knowledge gap is critical because aquaculture products are a growing source of protein and are widely consumed. Therefore, surveillance of parasite in farm fish is important for both public health and for the sustainability of the aquaculture industry. And let us take a look at the introduction. As I said before, anisakiasis is caused by the larval stage of Anisakis nematode, and this parasite have a complex life cycle, as you can see, and that involves several types of hosts. The adult worms usually live in the stomach of marine mammals, such as dolphins and whales, which are the definitive hosts. Eggs release into the water, hatch, and free-swimming larvae will be ingested by small crustaceans such as copepods. And these serve as the first intermediate host. When small fish or squid consume the infected crustacean, the larvae migrate into their tissues, and these animals act as paratenic or transport hosts. A larger predatory fish may also acquire infection through the food chain. Human, on the other hand, is an accidental host. When raw or undercooked fish is consumed, the larvae cannot complete their development, but they may cause gastrointestinal disease or allergic reaction. And this cycle highlights the importance of understanding the epidemiology of anisakis, not only in wild marine fish, but also in aquaculture species, since the latter are widely consumed and expected to be safe for human consumption. Now let us take a look at the problem statement. First, although aquaculture systems are generally considered safer, there is evidence that anisakid larvae can still be found in farm fish. This raises questions about possible transmission routes such as contaminated feed and seawater exchange with coastal environment. Second, the presence of anisakis in food products is a direct concern for food safety. These larvae are zoonotic and may cause disease or allergic reaction in humans. Since aquaculture products are widely consumed, consumer trust and market sustainability depend on ensuring their safety. The aim of this study was to investigate the epidemiology of anisakis larvae in farm fish collected from aquaculture zones across peninsular Malaysia. So in this study, a total of 140 farm fish were collected from aquaculture farms located in Penang and Langkawi, two important aquaculture zones in peninsular Malaysia. And the samples include 3 commonly farmed species, Ocean sea bass, snappers, and groupers. And overall, the sample fish weighed between 0.1 to 1.0 kg, which is the commercial size. As for methodology, to detect the anisakid larvae, we employ a combination of morphological, microscopic, and molecular approaches. First, morphological observation focus on the features such as larva size and shapes, the ventriculus, and the presence of boring teeth. Second, scanning electron microscopy provide detailed visualization of key diagnostic structure, especially the boring teeth and the micron of the larva tail. And finally, molecular identification targeted the internal transcribed spacer region, and a primer published by Zhu et al. And Kun et al. Were used to amplify this marker, ensuring accurate species confirmation. Now we go to the result and discussion. In this study, we first examined the larvae under light microscopy to determine their morphological features. On the left, you can see the specimen that was isolated from the fish sample. Under higher magnification, as shown in the middle image, we observe the presence of boring teeth at the anterior end. Additionally, as shown in the image on the right, the specimen has clearly visible ventriculus, a structure that connects the esophagus and the intestine. The presence of both the ventriculus and these distinctive boring teeth strongly supported the classification of the specimen under the family Anasakidae. This provides morphological evidence that the larvae recovered from farm fish in aquaculture zones are indeed anisakid nematode. So the molecular part, to determine the species identity of the anisakis larvae recovered from farm fish, we perform molecular sequencing and blast analysis targeting the ITS region. The query sequence showed high similarity to multiple entries of Hysterothylasium amoyense, with percent identities exceeding 98% and a value of 0.0, indicating highly significant matches. The top hits consistently align with the isolates from same genus and species, confirming the taxonomic placement. Morphological observations were consistent with third stage larvae, L3, supporting the molecular identification. The presence of Hysterothylacium amoyense in farmfish raised several important considerations. Although the Hysterothylacium species are not traditionally classified as major zoonotic threats, some cases of accidental human infection have been reported, particularly through consumption of raw or undercooked fish. Experimental study in mammalian models, such as mice, have shown histopathological changes upon infection with H. amoyense, suggesting potential pathogenicity. However, the zoonotic potential of amoyense remains limited and poorly documented, and it is currently not considered a significant public health concern. From food quality perspective, the reddish appearance of the larvae may affect consumer perception and marketability, especially in fresh or minimally processed seafood. And these findings highlight the importance of parasite monitoring in aquaculture, not only for health assessment, health risk assessment, but also for maintaining product integrity and consumer confidence. In summary, while amoyense may not pose a major zoonotic threat, its presence in farm fish warrants attention due to potential food quality issues and the need for continuous surveillance, especially in Malaysia aquaculture zone. Take a look at the prevalence. Now we examine the prevalence of Heterothylacium amoyensis across the 3 farm fish species included in the study. Starting with Latus calcarifer or sea bass, we observe a prevalence rate of 7.1%, which is 3 out of 40 individuals infected. And as for snappers, the prevalence was lowered, only 2.5%, with only 1 out of 40 infected. And interestingly, for groupers, showed no detectable infection among the 60 species examined. In terms of parasite burden, the mean intensity was consistent across infected individuals, 1 larvae per fish, indicating low level of infestation even in positive cases. This finding suggests that while amoyense is present in farm population, its prevalence and intensity means relatively low. The absence of infection in groupers may point to the species-specific resistance or differences in farming practices, such as feed composition or environmental condition. Overall, these results are encouraging from a food safety perspective, but they also underscore the importance of continued surveillance, especially in species like sea bass that show higher susceptibility. Taken together, the molecular confirmation, species-specific prevalence, and food safety implication of Hysterothylacium amoyense in farm fish highlights the need for proactive monitoring in aquaculture system. Now, let me summarize the key takeaways and recommendations from these studies. Hysterothylacium amoyense was identified in farm fish using molecular and morphological methods. And although its zoonotic potential is limited, its presence may affect food quality and consumer perception. And species-specific prevalence suggests ecological factors may influence infection rates. Routine parasitological screening and molecular diagnostic should be integrated into aquaculture surveillance program. And last but not least, this finding contribute to the better understanding of parasite dynamics in Malaysian aquaculture and support effort to ensure seafood safety and sustainability. Let them say goodbye. a bit, yeah. Yes, thank you. This is the team, and Dr. Kwa, as you can see there, trained in parasitology. Me, only in molecular biology. I'm not good in diseases. If you ask me anything, I just can refer your question to Dr. Kwa. And yeah, we also have somebody that trained in fish taxonomy. Thank you.
Thank you for a very clear presentation. Are there any questions from the floor? Andy.
Thank you very much. Nice presentation. A quick comment. Did you do tissue digests?
No, we don't.
Because tissue digests will probably reveal more larvae, which will probably change some of your figures. And the second thing, can I request that when you do your analysis of the different fish, can you also please look at the size and the age at which the fish was stocked? Can you also look at the feed management? Because most of these fish get infected when you either you stock very small fish and they just nibble the crustaceans when they come through. So the way to address that is to make sure you have good feed management, but also to stock a larger fish. And then hopefully you can begin to address some of the food safety issues.
Thank you. Actually, that's what we did for wild-caught fish. For wild-caught fish, we do a range of size because what we found, a matured fish have higher susceptibility. But for farm fish, this is just a starting because we thought that area always have a sighting of dolphin. So we thought maybe, just maybe there will be this anisakis along that route. So that is why we're doing it. So maybe, yes, in the next phase, we can do that. Thank you.
Any further questions from the floor? One just here.
Yeah, thank you very much. My question is very similar to Andy. So from our experience, in fresh fish, the part usually...
Could you just hold the microphone a bit closer?
Okay. Anisakis larvae usually we found in the digestive organ, but in the old fish, mostly we found in the muscle. Yeah, so maybe you had a better to examine both, muscle if you use old fish, but if fresh fish, maybe just only the digestive organs.
Yes, I understand. Thank you for the suggestion. Yes, for Anisakis simplex, that's what happened, right? When they are, the time when they caught, they will go straight to the bone and the muscle. But our experience with Typica, nothing. They are not going to the muscle. But we are very not have much information on Amoyense yet. So yes, again, maybe we can go to that area also. Thank you.
Any further questions from the floor? Do you have any idea what the intermediate host is in your situation?
Again?
Do you have any idea what the intermediate host is in your situation?
You mean the host for...
That is bringing the Anisakis into the cages.
Oh,
It requires an intermediate host,
yes.
doesn't it?
Actually, we maybe two possibilities. One is, as I said, a dolphin along that area. And the one is, they sometimes give trash fish to the farm fish. So maybe that's the cause of the infected by that trash fish, yes.
Okay. Thank you very much for an excellent talk. My co-chair has deserted me to return home. So, the next speaker is going to talk about the epidemiological profile of an infectious hypodermal and hematopoietic necrosis virus in farm Peneus monodon in West Bengal in India. And that's Dr. Anne-Marie. And I'm really sorry, I managed to find a bio of everybody else on the web, but not you. So if you'd like to introduce yourself, thank you. This is a different, this is a different presentation. This one's by Dr. Uma. Dr. Uma is Professor and Head of Department at Aquatic Animal Health Management in the Dr. MGR Fisheries College and Research Institute in Poneri. And I wondered who MGR was, and Marutur Gopala Ramacharan was an actor and film producer and a state governor in your state. So, yeah. And the floor is yours. The presentation is... the presentation is...
Tilapin viruses, molecular surveillance, and environmental correlates in the wild, and tilapia culture farms in Tamil Nadu, India. Thank you, sir.
Perfectly on cue.
Yeah.
Thank you.
Yes. Yeah, good evening, everyone. So that was the topic of my presentation. And tilapia is the second most widely farmed fish globally, with a global production of 5.3 million tons as per FAO statistics 2024. And the predicted global market value is about $9.2 billion by 2027. And although we don't find India in the list of top 10 tilapia producers, India produced tilapia to a tune of 70,000 metric tons in 2022. And there is interest in the culture of genetically improved farm tilapia and Nile tilapia in aquaculturists in India. And the targeted tilapia production of India for the year 2027 is 0.766 million metric tons, and that for 2032 is 2.155 million metric tons. And as for any other aquaculture operations, the major threat to the development and expansion for tilapia farming is diseases, and the annual production losses and also the commercial loss due to this diseases is estimated to be around $1 billion. And although tilapia is considered hardy and resistant to various environmental changes, there is a susceptibility to bacterial, viral, fungal, and parasitic infections in intensive tilapia culture operations. And to date, 8 viral diseases have been reported to infect tilapia. But viruses are undoubtedly the major pathogens because we have very limited antiviral therapeutics and vaccines available for their control and treatment. And recently, 2 viruses that specifically infected tilapians have been reported globally, and they are tilapia lake virus and tilapia parvovirus. And tilapia lake virus, it belongs to the family Orthomyxoviridae and genus Tilapin virus, and it's a negative sense RNA virus with 10 genomic segments, and hence there is a high probability of evolution of virulent strains due to viral reassortment. And this was first reported in the year 2014 in Israel, and later it has spread to various countries in 3 different continents. It was first reported in India in the year 2018. And tilapia causes very high mortality, up to 90% in the infected stocks, and hence WAH has listed that in an emerging pathogen list, and TALV is non-zoonotic in nature. And tilapia parvovirus is a single-stranded DNA virus of family Parvoviridae and genus Chaparvovirus, and it was first reported in the year 2019 in China and 2021 in Thailand, and India was the third country to report this disease. And we have 4 objectives in this study. The first one is to investigate the prevalence of TALV and TIPV in Tamil Nadu as it is poorly understood, and to study the correlation between the disease outbreaks due to TALV and TIPV and the environmental factors and the co-infection status. Because to understand the epidemiological factors, we have to assess the correlation between these disease outbreaks and the epidemiological factors and their influence, and to develop sensitive and specific molecular diagnostic assays based on the sequences that have been generated in the indigenous viral strains that have been documented in the study. And for any effective disease management protocols, we need accurate assays for the detection of etiological agents. And to study the influence of these viruses on the host immunity and metabolic pathways by transcriptomic analysis was the 4th objective. So understanding the host-virus interaction by transcriptomics would greatly help to develop effective vaccines and treatment protocols. And this is about the project. This surveillance study was done under a Tamil Nadu state government funded project on e-fish health surveillance and monitoring network to improve fisheries production in Tamil Nadu. And under this project, we did surveillance in all the districts of Tamil Nadu, and we have 38 districts. And the results that I present here pertains only to the tilapia farming districts, which is about 14 districts were having active tilapia culture. And we identified 66 sampling sites, which not only included farms, but also wild sites, which was under the control of Tamil Nadu Fisheries Department. And the samples were collected from these sites at fortnightly intervals, and also during the disease outbreaks as emergency surveillance. And fish samples, both apparently healthy as well as the infected ones, were collected. And water samples were also collected from the ponds as well as from the wild water bodies. And about the methodology, the observations of the gross clinical signs were recorded on site, and molecular screening was done for the confirmation of the disease, and bacteriology was done for the isolation of the co-infecting bacterial pathogens, and the analysis of various water quality parameters were done, and some were done on site, like temperature and dissolved oxygen were recorded on site, and the other parameters were done in the laboratory. And this is a glimpse of the surveillance activities. And we recorded various clinical signs in the infected samples, and later they were confirmed to be infected with TILV or TIPV. And the samples were confirmed by molecular analysis, that is by PCR, following the published protocols. And we also attempted to amplify and sequence all the 10 genomic segments of TILV. But surprisingly, we found that the segment 1 could not be amplified in any of our isolates that we had got during the surveillance. And similarly, the NS1 and the VP1 genes of TIPV were also amplified and submitted to the GenBank for the benefit of other researchers. And these are some of the histopathological changes that we had observed in the TLV infected and TIPV infected samples. And we could see histopathological changes in the liver, kidney, and spleen in case of TILV infected samples. And in case of TIPV, we also observed changes in gills and also in spleen. And our prevalence data showed that about 51.55% of the total sites that we were brought under surveillance had TILV, followed by 10.5% of TIPV. And dual infection with TILV and TIPV were also reported in 6.06% of the sites that were surveilled. And for the next objective on studying the correlation between TILV, TIPV disease outbreak and co-infection, we had isolated the co-infecting bacterial pathogens, which included Aeromonas veronii, Streptococcus agalactiae, Pseudomonas species, and Enterococcus species. And our observation showed that high mortality rates were coinciding with the sites that had multiple bacterial co-infections, underscoring their potential role in increasing the disease severity. And score matrix of individual variables were prepared for principal component analysis, and the scores were given based on the severity of the disease in fish samples and the environmental parameters recorded in the corresponding sites. And the core plot analysis showed the contribution of each of these variables towards the dimensions, 3 dimensions in TILV infection. And this is a biplot that shows that environmental factors and co-infections as critical drivers of TILV outbreaks. And you can see the clustering of data points of this TILV positive samples at low temperatures and also co-infections and by the presence of these syncytial cells. And these indicate that environmental fluctuations and co-infections can trigger viral activity, resulting in high mortality rates. And for the third objective on development of molecular diagnostic assays based on the sequence information of the indigenous viral strains documented in the study, we had developed 3 different molecular assays for specific detection of these 2 viral pathogens. And for TILV, we have developed RT-LAMP and multiplex PCR assay. And for TIPV, we developed a nested PCR assay for accurate detection. And LAMP, or loop-mediated isothermal amplification technique, is one of the fastest nucleic acid amplification methods, and it has various advantages, like it is very easy to perform, it is much cheaper and cost-effective, and does not need any expensive equipments, and does not need any specialized skills to perform the test. And all we have to do is to mix the DNA or a template DNA along with the reagents that we have, which has basic reagents along with the enzyme. And we have to maintain the tubes at 65 degrees for 30 minutes. And at the end of the reaction assay, you can see the color change, based on which you can identify the positive and the negative samples. And this is an ideal field assay. And we have also standardized the visual detection methods to make it much easier with hydroxynaphthol blue, calcine, and also cyber green. And the detection limit of this assay is 1 picogram of template RNA. And this is a multiplex kit that we have developed for TILV, targeting the segments 2, 3, and 8. And we have selected these 3 segments because evolutionarily these are considered to be very stable and minimally affected by the assortment, making it as a reliable detection target. And this ROC curve, that is receiver operating curve, it has showed that the AUC value, that is area under the curve, to be 1, which is showing that it is 100% accurate in differentiating the false positives and the false negatives. And this is a nested PCR assay that we had developed for TIPV. This was targeting NS1 gene of this TIPV. And in-house validation was also done with the TIPV samples that we had collected during the surveillance. And this also had 100% accuracy with moderate sensitivity. And for the transcriptomic analysis of TILV-infected tilapia, we had collected the liver tissue from the healthy fish as well as from the infected fishes, and we did transcriptomic analysis. And this is about the transcriptomic sequencing and assembly, and you can see the genes that have been upregulated and downregulated, which are represented in red dots and blue dots, and the black dots represent the genes that were not significantly changed. And a total of 3,356 DEGs were detected, out of which 1,726 genes were significantly upregulated, and 653 genes were significantly downregulated. So the upregulated genes in this MAPK pathway showed that this highlighted the induction of host immune defense and inflammation, and this indicated stress, inflammatory, and apoptotic responses. Whereas the downregulated genes suggested that viral interference to suppress the protective signaling of the host and the host virus tug of war. And the upregulated genes of chemokine signaling pathway indicated strong host immune activation against the infection by showing the enhanced chemotaxis, leukocyte migration, increased cytokine production, and elevated ROS production and apoptosis. And the downregulated genes showed that decreased survival and inflammation responses in the cells. And the functional analysis of DEGs involved in the immune responses showed several proteins that are involved in protecting the host against this infection. And we have listed the list of proteins that are playing a major role. And TLV infections altered various genes in metabolic and immune-related pathways. And we have identified all those genes, and we have given the number of genes that were altered in the metabolic and the immune-related pathways. And I hope this results of this study will be helpful in developing the prevention and treatment strategies for these tilapian viruses. And I acknowledge the funding support from Tamil Nadu State Planning Commission and also under the National Agriculture Development Program for the implementation of this study. And I would also like to thank the organizers for the opportunity. Thank you.
Thank you, Dr. Umar, for sticking so well to time and presenting quite a complex study in so clearly. Are there any questions from the floor? No. I see no questions, so thank you very much indeed.
Yeah, thank you.
And our final speaker, I'm very sorry to have confused the two of you. It's getting late in the day.
Good evening, everyone. My name is Anne Mary. I am Junior Consultant, NASPAD, MPDA. My presentation is our work on epidemiological profile of infectious hypodermal and hematopoietic necrosis virus in farmed Penaeus monodon in West Bengal, India. The study was conducted by the team Quality Control Laboratory, MPDA, Kochi. Significance of my study. Infectious hypodermal and hematopoietic necrosis is one of the serious shrimp disease. Infectious hypodermal and hematopoietic necrosis is a causative agent of this disease. It's a small, non-enveloped single-stranded DNA virus infecting Penaeid shrimp and could be a reason for growth retardation and various deformities. Frozen shrimp is the foremost marine product export from India. Screening of shrimp is an important quality criteria for pre-export testing. WSSV and IHNV are regularly monitored by importing countries such as China, Korea, Saudi Arabia, Australia, etc. Aquaculture production in West Bengal during 2022 and 2025. The dominant species contributing the production in West Bengal is Lithopenes vanami, and 90% of production is Lithopenes vanami. And West Bengal aquaculture is mainly depend upon Lithopenes vanami with Penaeus monodon and Microbacterium rosenbergi. Objective of my study: detection of IHNV in Penaeus monodon collected from West Bengal, epidemiological profiling of IHNV in the district of West Bengal, North 24 Pragnas, South 24 Pragnas, East Medinipur, seasonal variation in the occurrence of IHNV in West Bengal to create a valuable baseline data for mapping of disease occurring areas in West Bengal. In addition to that, a species-wise comparison with the detection of IHNV. 3 districts of West Bengal selected for sampling during 2023 to 2024. Total 257 Penaeus monodon samples were collected. Other species such as Lithopenes vanami and Microbacterium rosenbergi collected from West Bengal. Sample size average 11 to 13 centimeter length and weight of 30 to 40 gram size were collected. Clinical signs were noticed and recorded. Clinical signs observed: opaque abdominal musculature, white to buff lashes under the carapace, reduced and irregular growth in juveniles and adults, reduced growth in size, deformed rostrum growing to one side, deformed 6th abdominal segment. Pleopods, gills, and tissues are extracted, fixed in ethanol for DNA isolation, and brought to the laboratory. Genomic DNA was extracted from pleopod, gill, and tissue using commercial kits. Conventional polymerase chain reaction was performed using specific primers of IHNV recommended by World Organization of Animal Health Manual. All IHNV amplicons were restricted in the region non-structural gene with an amplicon size of 309 base pair. The diagram depicts the step-by-step molecular diagnostic workflow starting from sampling to result interpretation. The table shows 257 monodon samples were tested and 29 samples were IHNV infection. On the other hand, 228 samples are free from IHNV infection. The percentage of positivity is 2.52%. The prevalence is low compared to other total samples screened. Other species like Penaeus monodon, Lithopenes vanami and Microbacterium rosenbergi are free from IHNV infection. The percentage of positivity is 2.52%. The prevalence is low compared to other total samples screened. Other species like Penaeus monodon, Lithopenes vanami and Microbacterium rosenbergi are free from IHNV infection. analysis of samples from West Bengal. The diagram shows samples collected from North 24 Pragnas and East Medinipur and South 24 Pragnas are the IH samples collected from. And North 24 Pragnas only shows the positivity rate in IHNV. Seasonal variation of IHNV detected during 2023 and 2024. In the diagram, November in 2023, November shows the highest sampling analyzed and highest positivity. In 2024, there is May is the highest rate of sampling and positivity. September and October are the common months during 2023 and 2024 year. Epidemiological profile of West Bengal. IHNV was detected only in 24 northern Pragnas at a low prevalence of 2.52%. No infection was found in South 24 Pragnas and East Purba Medinipur. IHNV presence is localized, not widespread in West Bengal. This is the graph shows the prevalence area detected in West Bengal. My study concluded that the presence of IHNV found to be low in the state of West Bengal, India. North 24 Pragnas districts had maximum positivity. Results suggest that the presence of potential localized endemic area within the West Bengal. Common clinical significance found in all three species was uneven growth within single crop. Maximum positive cases of IHNV detected during September to December period in 2023. Maximum positive cases of IHNV detected in May, September, October in 2024. The only species affect IHNV in West Bengal is Penaeus monodon. Special thanks to National Fisheries Development Board and the Department of Fisheries, the Marine Product Export Development Authority, National Surveillance Program for Aquatic Animal Diseases, and the National Bureau of Fish Genetic Resources, Central Institute of Backward Aquaculture, the organizers. Thank you.
Thank you for your presentation. So any histopathological data, your result is supported by any histopathology, have you done?
No, sir. We are mainly focused on molecular techniques.
Only PCR detection?
Yes, sir.
Okay.
Yes.
Why do you think that there is no prevalence in Anim and only in monodon?
We are using
area is same.
Yes, we are using specific pathogen-free seeds. That's why there is no IHNV introduction.
In Anim?
Yes.
Any further questions? Please go ahead. Okay. I have a question actually, and that is, you had, I think it's 1147 samples.
Yes, sir.
And when you showed the map, there seemed to be a lot fewer data points on the map. I may have missed it, but do you collect it from, where, was the collection from ponds or from farms? What was the unit of study?
We are collected from farms.
And how many ponds were there?
Samples are collected from West Bengal. Their samplers are there. They are collecting and brought to our laboratory.
Okay. There's a question there in the back.
You have presented that the black tiger product Penaeus monodon produced 67,000 ton in 2024 and 25. Is it culture or is it capture?
Sorry, sir?
You have shown na, that is Pineus monodon was, total production was 67,000 ton. Is it culture or capture?
This is total production.
Production and what? That is culture fisheries? Culture species or capture species? Natural production or the...
The data from West
That
Bengal.
enter India. 1,18,000 Pineus
The production rate
the total
from
India or whole West Bengal?
They're from India.
Oh.
Okay, I think we can clarify this over tea. Can I thank the audience and all the speakers for their participation in this session. We inherited a 30-minute deficit, and we ended up with a 30-minute deficit. So, in fact, everybody in this session kept very well to time. So thank you very much indeed.